Okay, question 3. So we have a distance versus time graph. It's of a dog. And so now we want to calculate velocity. So velocity is going to equal slope on this because velocity is going to be our position over our time. And so we've got our position, we've got our time. So we need slope. So from 0 to 1 second, I can see that the rise is 10. So I've got 10 meters over 1 second. So that means 10 meters per second positive. From time 1 to 2 second, the position doesn't change. So it's 0 meters over 1 second, and that means the speed was 0 meters per second. From 2 to 5, I can see I have the same slope here. And so it looks like we're going from 10 to 40. So that's a change of 30 meters on top. That's my rise. And that happened over 3 seconds. And therefore, I'm back at that 10 meters per second. And then in the last second, it goes from 40 meters down to 0. And I can tell that this is a negative slope. So I'm going to want to make sure that however I do this calculation of rise over run, when I'm done, I should end with a negative value. So I'm going negative 40 meters in 1 second. And so then I have minus 40 meters per second. So that's how we get velocity from a position graph. The velocity versus time graph represents an object's motion. Determine the acceleration. So when we have velocity versus time, then the slope of this graph is our acceleration because velocity is the change, acceleration is the change in velocity per time. So from 0 to 5 seconds, I can see that my speed changes by 50 meters per second in the positive direction, and that's over 5 seconds. And so I end up with 10 meters per second squared as my acceleration. Then I can see from times 5 to 7, my velocity isn't changing, so I've got 0 acceleration. And then once again, I can see in the negative direction, so it goes from 50 down to 0, and it only takes 1 second. So it's just going to be a change of 50 over 1 second, and so it's minus 50 meters per second squared. Okay, so the key things here are that we should be able to calculate slope, and we should pay attention to if it's positive or negative. Now, how do you determine distance from a velocity time graph? Well, we should know that velocity is distance over time. So what is distance? If I rearrange this equation, I can get distance equals velocity times time. So if I do velocity times time, I should get my distance. Well, that's equal to area on this graph, right? So the velocity is the height and the time is the length. And so if we get the area of underneath this curve, we'll know the distance. You kind of have to break it down into different sections. The time 5 to 7 is the easiest. It's like a rectangle, and so it's got a 2-second base, and it has a 50 meters per second height. So that section is going to have 50 meters per second times 2 seconds. And so during that section, the person or the object traveled 50 meters. So that's like section 2. The other 2 sections are triangles. And so when you do triangle, the area is equal to 1/2 length times width, or length times height, whatever descriptors you want to use. So for this first big triangle, it has a base of 5 seconds, and it has a height of 50 meters per second. But then we need to multiply that by 1/2 because it's a triangle. And so 5 times 50 is 250, and then I half that, and I get 125 meters in that first triangle. So that one's 125. This one is 100, and the last one I can tell is going to be the smallest. It's also a triangle, so we're going to get 1/2. It's got a base of 1 second, and it has the height of 50. And so 1 times 50 is 50, times 1/2 is 25 meters. So this object traveled 125 meters over the first 5 seconds. Then it traveled 100 meters over the next 2 seconds. And then it traveled 25 meters in this last second. And so in total, the object traveled 250 meters as its total distance. Okay, the below motion graph shows the speed of a car over time. At time 0, an animal, now I understand. At time 0 seconds, an animal runs into the road 50 meters in front of the driver. So what was the car's initial velocity? Well, I can see initial means at time 0, and the car is traveling at 20 meters per second. Remember that that's not kilometers per hour, so 20 meters per second is actually a pretty fast speed. How long did it take the driver to react and hit the brakes? Well, it looks like the car doesn't start slowing down for a second, right? This is where the car starts slowing down. So I would say that the reaction time was about 1 second. And how long did it take the car to stop? Well, from that point, it took another 2 seconds for the cars to stop. So it took 2 seconds from hitting the brakes, and it took 3 seconds total from seeing the animal. So I know the car is stopped when its speed goes to 0. Okay, what was the acceleration of the car as it slowed down? Okay, well, again, I'm going to look at slope here to get acceleration from a speed and time graph. I can see it goes from 20 down to 0. So its speed is dropping by 20 meters per second. I'm going to make that negative. And that happened over 2 seconds. So it was negative 10 meters per second squared. It's just coincidence that a lot of these questions are having speeds and accelerations that are 10. The numbers being used here are pretty simple. So be prepared to use more complicated numbers with the calculator. Okay, if the car weighed 1,500 kilograms, what was the net force acting on the car during this time? Well, we know that net force equals mass times acceleration. I've got the acceleration from the previous question, and so I can do 1,500 kilograms for the mass times negative 10 meters per second squared, and so that would equal to negative 15,000 newtons as the net force acting on that car. How far did the car travel after the driver saw the animal, and did the driver hit the animal? So remember, distance is based on area of a speed versus time or velocity time graph. So I got to break this into my 2 sections. I'm going to get this area, and then I'm going to get this area. So the first area looks like the bottom is 1 second, and the height is 20. So the first area is just 1 second times 20 meters per second. That means they traveled 20 meters in that first part. And in the second part, it's a triangle, so it's 1/2, and then it's 2 seconds long, and it's 20 meters per second high. So that's 1/2. 2 times 20 is 40, and then 1/2 is 20. And so in total, the driver traveled 40 meters, and so they did not hit the animal because we said the animal was 50 meters away. Now, let's draw a new line on the graph to show a car with a drunk driver. Drunk driver has a higher initial speed, 30 meters per second, and the reaction time is slower, 1.5 seconds. So they start off about here, and they don't start stopping until here. And then it says the same deceleration as the first car. So that means it should have the same slope. So it should look parallel. And I'm just sketching. I don't know exactly where it's going to hit, but it would be something like that. It should look like the same slope as that other one. The key difference is that it has a higher initial speed. So here's 30, and that it doesn't start slowing down until time 1.5. Okay. And now I guess a follow-up question, which I don't see on this thing, would be, does this person hit the animal? So if you're going to do this one, you'd have to do that the area here is 30 meters per second times 1.5 seconds. So that's 45 meters, and I think we're pretty sure it's going to hit this animal because it's gone 45 meters before it even hits the brake, before the person even realizes that there's an animal and they want to stop. They've already almost hit the animal. And then in the second section, well, let's guess, I guess it was 10 meters per second. It's going to take 3 seconds, so it should hit right here at 4.5. So 3 seconds and 1/2, and it's going down to 30, so it's half a night, so it goes another 45 meters. So this person wouldn't be able to stop their car for 90 meters, and that, my friends, is going to be a dead animal. Okay? Let's say it was a bunny. Okay, they're not happy. So yeah, things like drinking or being tired or being on your phone are going to give you additional reaction time, and they're going to make it slower and harder for you to actually stop than compared to someone who's paying attention and following the rules.